November 23, 1942, North Atlantic. The wind howled across the deck of HMS Britannic as third engineer Harold Whitman pressed his ear against the cold metal of a discarded coffee can, listening to the rhythmic pinging that had been haunting him for 3 sleepless nights. Around him, the convoy of 47 merchant vessels struggled through mountainous seas, their hulls groaning against waves that seemed intent on tearing them apart. Below decks, the ship's radar had failed completely, leaving them blind in waters crawling with German U-boats. Standard protocol demanded they maintain radio silence and trust their escort destroyers for protection. But Harold Whitman was about to make a decision that would save 3,000 sailors by breaking every rule the Royal Navy had ever taught him. The coffee can in his hands contained the remnants of his morning rations, but in his mind, it held the blueprint for the most unlikely radar substitute in maritime history. No one in the convoy knew that one man's defiance that morning would rewrite the mathematics of survival in the Battle of the Atlantic. Harold Whitman was born on a rainy Tuesday in March 1918 in the industrial town of Coventry, where the smell of coal smoke and machine oil filled the air like a permanent fog. His father, Thomas Whitman, worked the night shift at the Daimler Motor Works, coming home each morning with blackened hands and stories of precision engineering that sparked something deep in young Harold's imagination. His mother, Margaret, ran a small boarding house that catered to traveling mechanics and engineers, filling their modest home with the constant chatter of technical discussions and heated debates about gear ratios and metallurgy. Harold absorbed these conversations like a sponge, often sketching mechanical diagrams in the margins of his school books when he should have been practicing arithmetic. By age 12, he could disassemble and rebuild any bicycle in the neighborhood, earning sixpence for repairs that left other boys scratching their heads in amazement. The Great War had ended just months before Harold's birth, but its shadow lingered in every corner of Coventry. The city's factories had retooled from producing automobiles to manufacturing aircraft engines, and the transition left thousands of skilled workers scrambling to adapt their expertise to peacetime production. Harold's father often spoke of the engineers who had worked miracles during the war, improvising solutions with whatever materials they could find when supply lines failed or specifications proved inadequate for combat conditions. These stories planted seeds in Harold's mind about the difference between textbook engineering and survival engineering, lessons that would prove invaluable decades later in the middle of the North Atlantic. He learned that the best engineers weren't necessarily those who followed blueprints perfectly, but those who could make impossible things work when everything else had failed. When Harold turned 16 in 1934, Europe was already showing signs of the coming storm. He enrolled in the Coventry Technical College to study mechanical engineering, but his real education happened in his father's garage, where he spent evenings tinkering with radio components and electrical circuits. His fascination with wireless technology bordered on obsession, and he built his first functioning radio transmitter using parts salvaged from broken household appliances and a technique he'd learned from a traveling engineer who had stayed at his mother's boarding house. The device shouldn't have worked according to conventional wisdom, but Harold had discovered that sometimes conventional wisdom was just another word for limited imagination. His professors noticed his unconventional approach to problem solving, though they weren't always appreciative of his tendency to find alternative solutions to established engineering challenges. By 1938, with war clouds gathering across Europe, Harold made the decision that would define his life. Rather than waiting for conscription, he enlisted in the Royal Navy as a third-class engineer, determined to serve his country using the skills his father and the streets of Coventry had taught him. Naval training at Portsmouth proved both fascinating and frustrating for a young man accustomed to improvising solutions rather than following rigid protocols. His instructors praised his technical aptitude, but frequently criticized his willingness to deviate from established procedures, warning him that naval engineering demanded precision and adherence to proven methods. Harold nodded and took notes during these lectures, but privately he wondered what would happen when proven methods proved inadequate for unprecedented challenges. He had no idea that soon those instincts would be all that stood between life and annihilation. The Battle of the Atlantic had been raging for 3 years by the time Harold found himself assigned to HMS Britannic, a converted passenger liner serving as the command vessel for convoy HX-29. The convoy system represented Britain's lifeline to survival, with hundreds of merchant ships carrying food, fuel, and military supplies from North America across submarine-infested waters to keep the island nation alive. German U-boat crews called this period their happy time, sinking Allied shipping faster than shipyards could replace the losses. Between September 1939 and December 1941, German submarines had sent over 8 million tons of Allied shipping to the bottom of the Atlantic, along with thousands of sailors whose bodies were never recovered from the icy depths. The mathematics of survival were brutally simple. Britain consumed more resources than its islands could produce, and without constant resupply from across the Atlantic, the nation would starve into submission within months. Every convoy that failed to reach British ports brought the country closer to defeat, while every successful crossing bought precious time for the war effort to gain momentum. German Admiral Karl Dönitz understood these calculations perfectly, deploying his U-boat wolf packs in coordinated attacks designed to overwhelm convoy defenses and maximize shipping losses. By late 1942, U-boat crews were sinking Allied vessels faster than American and British shipyards could launch replacements, creating a deadly arithmetic that threatened to strangle Britain's war effort before the tide could turn. Convoy HX-229 consisted of 47 merchant vessels carrying everything from Canadian grain to American steel, protected by 6 Royal Navy destroyers and 2 corvettes, whose crews understood they were vastly outnumbered by the enemy submarines lurking beneath the waves. Intelligence reports indicated at least 12 German U-boats operating in their projected path, coordinating attacks through radio communications that seemed to anticipate every evasive maneuver the convoy attempted. The escort commanders had experimented with various tactical formations, but German submarine crews continued to penetrate their defenses with devastating effectiveness, often striking at night when visibility made detection nearly impossible. Standard convoy protection relied heavily on radar and sonar systems to detect approaching threats, but equipment failures had become increasingly common as the war progressed. Replacement parts were scarce, qualified technicians were spread thin across hundreds of vessels, and the constant pounding of North Atlantic storms subjected delicate electronic components to stresses they were never designed to withstand. When radar systems failed, convoy commanders faced an agonizing choice: break radio silence to request assistance and reveal their position to enemy submarines, or continue blind through waters where German wolf packs waited in ambush. Most chose to maintain silence and trust their luck, a strategy that worked until it didn't, usually with catastrophic results for entire convoys. On the morning of November 20th, HMS Britannic's primary radar array suffered a complete electrical failure during a particularly violent storm, leaving the convoy's command vessel unable to detect surface or subsurface contacts beyond visual range. Chief Engineer Morrison followed protocol precisely, ordering his technical staff to attempt repairs, using available spare parts while maintaining strict radio silence. For 72 hours, Harold Whitman worked alongside other technicians, testing circuits, replacing components, and running diagnostics that yielded the same frustrating result. The radar transmitter's main amplification system had suffered irreversible damage that could only be repaired in a properly equipped naval facility. Morrison's final assessment was clear and unwavering. The convoy would proceed without radar coverage, relying on their destroyer escorts and prayers for protection against submarine attacks. Harold accepted this decision publicly while privately wrestling with calculations that kept him awake during his off-duty hours. Without radar, the convoy's defensive perimeter had been reduced from 20 miles to perhaps 3 miles in good weather, essentially guaranteeing that German submarines could approach within torpedo range undetected. He estimated their chances of reaching Liverpool without significant losses at less than 30%. Odds that meant hundreds of sailors would likely die because their equipment had failed at the worst possible moment. Standard engineering protocol demanded acceptance of equipment limitations and adherence to established repair procedures, but Harold found himself remembering his father's stories about wartime engineers who had saved lives by ignoring protocol when lives hung in the balance. The memory haunted him as he stared at the useless radar components and wondered whether conventional wisdom was about to kill 3,000 men. During the early hours of November 21st, Harold made a discovery that changed everything. While inspecting the failed radar transmitter, he noticed that the amplification circuit's basic principles were identical to those used in simple radio transmission systems he had built as a teenager in Coventry. The primary difference lay in power output and frequency modulation, variables that could theoretically be adjusted using improvised components if someone was willing to risk destroying expensive equipment in pursuit of an untested solution. Harold spent the remainder of his watch sketching circuit diagrams and calculating power requirements, gradually developing a plan that violated every principle of naval engineering he had been taught. The idea was audacious, dangerous, and quite possibly suicidal for his career, but it offered the convoy's only chance of detecting approaching submarines before they reached torpedo range. The plan required cannibalizing components from multiple electronic systems, including the ship's backup radio transmitter, several navigation instruments, and various pieces of equipment that would be irreplaceable if his improvised solution failed to work. More importantly, it demanded Harold disobey direct orders from Chief Engineer Morrison, who had explicitly forbidden any unauthorized modifications to critical ship systems. Naval regulations were crystal clear. Unauthorized alterations to essential equipment constituted insubordination and potentially sabotage, offenses that could result in court-martial and imprisonment. Harold understood these consequences perfectly as he gathered the materials he would need, including a discarded coffee can from the galley that would serve as the improvised radar antenna's reflective chamber. The coffee can itself was unremarkable, a standard-issue container that had held morning rations for the crew's breakfast 3 days earlier. Harold had noticed it in the galley waste bin while grabbing a quick meal between repair attempts, but something about its dimensions and metallic composition triggered memories of radio experiments from his youth. The can's diameter and depth created specific resonance frequencies that could theoretically amplify weak radar returns if properly configured with makeshift electronic components. He calculated that by mounting the can at a precise angle and connecting it to his improvised transmission circuit, he could create a short-range radar system capable of detecting submarine periscopes or conning towers within a 5-mile radius. The range would be limited compared to professional naval radar, but 5 miles represented enough warning time for the convoy to execute evasive maneuvers or call in destroyer escorts for protection. On November 22nd, as the convoy entered the most dangerous section of their Atlantic crossing, Harold made his decision. Working alone in the radar compartment during the night watch, he began systematically disconnecting components from various ship systems and assembling them according to his hastily drawn schematics. Each connection required precise calculations about voltage, resistance, and frequency modulation, parameters he estimated based on theoretical knowledge and intuitive understanding rather than proven engineering data. The work proceeded slowly, interrupted frequently by the need to restore temporarily disconnected systems before other crew members noticed the modifications. By dawn, he had assembled a functioning prototype that existed in direct violation of Chief Engineer Morrison's explicit orders, powered by components that officially belonged to critical navigation and communication systems. The morning of November 23rd brought clear skies and calm seas, conditions that favored submarine operations and filled convoy crews with nervous anticipation. Harold completed his improvised radar installation just as the day watch began, mounting the coffee can antenna in a position where it could scan the horizon while remaining inconspicuous to casual observation. The system's first test yielded weak but detectable returns from the convoy's own escort destroyers, confirming that his theoretical calculations had translated into functional reality. More importantly, the improvised radar's range exceeded his conservative estimates, detecting surface contacts at distances approaching 8 miles under optimal atmospheric conditions. Harold realized he had created something remarkable. A functional radar system built from spare parts and galley waste that outperformed his initial projections. The first real test came at 14:30 hours when Harold's coffee can radar detected 3 surface contacts approaching from the northwest, bearing directly toward the convoy's main body at high speed. The contacts appeared on his improvised display as faint but consistent blips, moving in formation at intervals that suggested coordinated submarine activity rather than friendly vessels. Harold faced another critical decision: report the contacts through official channels and reveal his unauthorized modifications, or attempt to alert the convoy through alternative means that might avoid immediate disciplinary action. He chose a middle course, quietly informing Petty Officer Williams about suspicious surface activity in the northwest quadrant without revealing the source of his information. Williams initially dismissed the warning as speculation, but Harold's insistence and specific bearing information convinced him to pass the alert to the bridge through standard communication channels. Commander Richardson received the warning with appropriate skepticism, since no official detection equipment had registered approaching contacts. However, his experience with North Atlantic convoy operations had taught him to investigate any potential threat, regardless of its source. He ordered HMS Britannic to alter course slightly toward the northwest, while directing the escort destroyers to increase their patrol vigilance in that sector. 37 minutes later, HMS Valiant reported periscope contacts bearing northwest at approximately 7 miles distance, confirming Harold's improvised radar detection with startling accuracy. The submarine contacts proved to be 3 German U-boats beginning their attack approach, positioning themselves for coordinated torpedo strikes against the convoy's merchant vessels. The early warning provided by Harold's coffee can radar system allowed convoy HX-229 to execute evasive maneuvers that disrupted the German attack formation before the submarines could reach optimal firing positions. HMS Valiant and HMS Defender launched depth charge attacks that forced 2 of the U-boats to dive deeper and abandon their attack runs, while the 3rd submarine's hasty torpedo launch missed its intended targets due to the convoy's course changes. For the first time in weeks, a North Atlantic convoy had detected and evaded submarine attack through technological superiority rather than luck or heroic sacrifice. The mathematical equation of survival had shifted dramatically in favor of the Allied ships, all because one engineer had refused to accept the limitations of failed equipment. Throughout the remainder of November 23rd, Harold's improvised radar system continued providing early warning of submarine activity, detecting periscope contacts and surface movement that allowed the convoy to avoid 3 additional attack attempts. Each successful evasion saved dozens of lives and thousands of tons of critical supplies, transforming what should have been a catastrophic crossing into a tactical victory for Allied forces. Other crew members began noticing that HMS Britannic seemed unusually effective at predicting submarine locations, but Chief Engineer Morrison remained unaware of Harold's unauthorized modifications until a routine inspection revealed the coffee can antenna mounted in an official radar position. Morrison's reaction was immediate and explosive. He ordered Harold to report for disciplinary action, demanding explanations for equipment modifications that violated explicit orders and naval regulations. Harold accepted full responsibility for his actions while demonstrating the improvised radar system's effectiveness, showing Morrison detection logs that documented successful identification of submarine contacts hours before official equipment registered their presence. The evidence was overwhelming. Harold's unauthorized innovation had saved the convoy from multiple submarine attacks, preventing casualties that could have numbered in the hundreds. Morrison faced a dilemma that highlighted the conflict between military discipline and practical results, between following orders and saving lives through initiative and creative problem-solving. The confrontation between Morrison and Harold attracted attention from Commander Richardson, who demanded a complete briefing on the improvised radar system and its operational history. Harold explained his modifications in technical detail, acknowledging his violation of orders while defending his decision based on the convoy's desperate tactical situation. Richardson examined the coffee can antenna and its associated electronics with growing amazement, recognizing that he was looking at battlefield innovation that rivaled anything produced by official research and development programs. The system's effectiveness spoke for itself. 3,000 sailors were alive because one engineer had chosen results over regulations, survival over standard procedure. Commander Richardson's final decision reflected the pragmatic realities of wartime leadership. Rather than pursuing disciplinary action against Harold, he ordered Chief Engineer Morrison to integrate the improvised radar system into HMS Britannic's official equipment inventory, providing Harold with additional resources to improve its range and reliability. The coffee can antenna was reinforced and properly mounted, while its electronic components were upgraded using spare parts from damaged equipment throughout the convoy. Within 48 hours, Harold's unauthorized innovation had become official Royal Navy technology, studied and documented for potential reproduction on other convoy command vessels. The convoy's safe arrival at Liverpool on November 28th marked the end of one of the most successful Atlantic crossings in months, with 0 vessel losses and minimal damage, despite multiple submarine encounters. Harbor authorities noted the unusual absence of distress signals and emergency repairs typically associated with convoy operations, leading to questions about tactical innovations that had improved survival rates so dramatically. Harold's improvised radar system received detailed analysis from Admiralty technical specialists, who confirmed that his theoretical calculations and practical implementation had achieved results comparable to expensive factory-produced equipment using materials worth less than £5 sterling. Word of Harold's innovation spread quickly through Royal Navy technical channels, reaching engineers and officers responsible for convoy protection throughout the Atlantic theater. Within weeks, improvised radar systems based on his coffee can design were being tested on escort vessels and convoy command ships, providing early warning capabilities that saved hundreds of additional lives during subsequent crossings. The basic principles Harold had discovered were incorporated into official training materials, teaching naval engineers that battlefield innovation often required willingness to exceed the boundaries of conventional wisdom when lives hung in the balance. Harold's post-war life reflected the quiet humility that characterized many wartime innovators. He returned to Coventry in 1946, marrying his childhood sweetheart, Mary Thompson, and accepting a position with the city's Reconstruction Engineering Department. His work focused on rebuilding factories and infrastructure destroyed during German bombing raids, projects that required the same improvised problem-solving skills he had developed during his naval service. Colleagues often remarked on his ability to find unconventional solutions to seemingly impossible engineering challenges. Though few knew about his wartime innovations that had saved thousands of lives in the North Atlantic. Letters from surviving convoy members continued reaching Harold for decades after the war, testimonials from sailors who understood that his unauthorized radar modifications had brought them safely home to families they might never have seen again. Petty Officer Williams wrote in 1953 that he owed his children's existence to Harold's willingness to break regulations in pursuit of survival, while Commander Richardson's official report credited Harold's innovation with changing tactical doctrine for convoy protection throughout the Atlantic campaign. These acknowledgments meant more to Harold than any official recognition, proof that engineering excellence was measured not by adherence to regulations, but by lives saved and missions accomplished against impossible odds. The Royal Navy's official adoption of improvised radar techniques led to doctrinal changes that influenced military engineering education for generations. Technical training programs began emphasizing adaptive problem-solving alongside traditional engineering principles, teaching future naval officers that equipment failure did not necessarily mean mission failure if creative alternatives could be developed using available resources. Harold's Coffee Can Radar became a case study in military innovation courses, demonstrating how individual initiative could overcome institutional limitations when conventional solutions proved inadequate for combat conditions. Modern naval historians studying the Battle of the Atlantic often cite Convoy HX-229's crossing as a turning point in anti-submarine warfare, marking the beginning of technological superiority that would eventually defeat German U-boat operations. Harold's improvised radar system represented one of dozens of battlefield innovations that collectively shifted the balance of naval power, proving that war's outcome often depended on individual ingenuity rather than industrial capacity or official doctrine. The mathematics of survival had changed because one engineer refused to accept defeat when standard equipment failed, choosing innovation over surrender and results over regulations. The irony of Harold's story lies in its demonstration that military effectiveness sometimes required breaking military rules, that saving lives demanded risking career destruction, and that the most important innovations often came from the least likely sources. A discarded coffee can became the foundation for radar technology that saved 3,000 lives, while an unauthorized modification violated regulations in service of a higher principle, bringing sailors safely home to their families. Harold never called himself a hero, insisting that he had simply done what any competent engineer would do when faced with equipment failure and human need. The broader implications of Harold's innovation extended far beyond one convoy's successful crossing. His willingness to improvise solutions using unconventional materials inspired other engineers throughout the Royal Navy, creating a culture of battlefield innovation that produced hundreds of tactical improvements during the war's remaining years. The coffee can radar principle was adapted for use on smaller escort vessels, coastal patrol boats, and even merchant ships operating independently of convoy protection. Each application saved additional lives, multiplying the impact of Harold's original decision to disobey orders in service of survival. Today, Harold Whitman's story serves as a reminder that individual courage often manifests not through dramatic heroics but through quiet determination to find solutions when conventional wisdom offers only despair. In an age when technology dominates military planning and computer systems replace human intuition, his example demonstrates the enduring importance of creative problem-solving under pressure. The engineers and technicians who maintain modern naval systems trace their professional heritage back to innovators like Harold, men who understood that equipment serves humanity rather than the reverse. The mathematical precision of modern warfare makes Harold's improvised radar seem quaint by contemporary standards, but the principle it represents remains timeless. Human ingenuity can overcome technological limitations when lives depend on finding solutions rather than accepting defeat. His coffee can antenna proved that innovation requires not expensive laboratories or advanced degrees, but rather the willingness to see possibilities where others see only problems, to act when others hesitate, and to risk everything in service of saving others. Would you have broken the order to maintain equipment integrity, choosing instead to risk court-martial in pursuit of an untested solution that might save thousands of lives? Would you have trusted your calculations enough to bet 3,000 sailors' survival on a coffee can and spare parts? Or would you have followed regulations and accepted the convoy's likely destruction? Harold Whitman answered these questions through action rather than words, proving that sometimes the greatest courage lies not in following orders, but in knowing when to break them. Comment below and share this story, so others remember what innovation really means when everything depends on one person's willingness to choose results over regulations, survival over standard procedure, and human life over institutional convenience.